Hello, everyone. Today we are going to continue with polynomials. We are mostly going to think about greatest common divisor of polynomials and how to find inverse of polynomials over different rings. So let me review first, and then I would give you some questions to think about. Okay, so let's start. Let's first recall the situation over integers again. I know you all know it, but let's just review that. So over integers for natural numbers or for integer numbers, for integers, we had division theorem. Which says for any two numbers, a and b, we can divide a by b. There would be a number q such that a minus bq is going to be r, where r is an integer between 0 and a. In other words, we can write it as, and b. In other words, it can be a can be written as bq plus r, where r was greater or equal than 0 and less than a. Right? That was one thing. And the second thing we knew about the integers, the second important thing was the Euclidean algorithm. I think you know it, but I just review it very fast. So when we have two numbers a and b and we want to find their greatest common divisor, one idea is to use the Euclidean algorithm. So for example, let's say we want to compute the greatest common divisor of 171 and 30. Okay. One way to do it is to divide 131 using division algorithm. We can divide it by 30. Okay, so 30 times 5 is going to be 150 plus 21. That would be the remainder. So if I divide 171 by 30, the remainder is going to be 21. So the next step of Euclidean algorithm is to divide 30 by 21. Well, 21 times 1 plus 9 is going to be 30. So the next remainder is 9. The next stage of the Euclidean algorithm is to divide 21 by 9. So 9 times 2 is 18 plus 3 is going to be 21. So the remainder now is 3. And finally, we can divide 9 by 3, and 3 times 3 is 9, plus 0, the remainder is 0. Look at the last non-zero number, it's 3. It means the greatest common divisor of 171 and 30 equals 3. Okay, that's the case for integers or natural numbers. Now there is something similar for polynomials. So we have the same theory for polynomials. When we have two polynomials, say a of x and b of x, two polynomials, we can divide a of x by b of x and we get some qx such that ax minus bx times qx is going to be our remainder. Let's show it with rx, where the degree of r is greater or equal than 0 and less than degree of b. And just like the previous case, we can write ax is equal to bx qx plus rx, with this condition on degree of r. And also we have similar Euclidean algorithm. We have Euclidean algorithm for polynomials in order to find the greatest common divisor, or sometimes they call it greatest common factor of two polynomials. So let's see an example. Suppose a of x is equal to x squared plus 7x plus 6. And b of x is equal to x squared minus 5x minus 6. Okay. And suppose we want to find greatest common factor or divisor of these two polynomials. I want to see what is that. Well, if you remember, when we want to compute the greatest common divisor of two numbers, there are two different ways. Either we can decompose those numbers to primes, or we can use the Euclidean algorithm. Here we can do both. So either I should say, let's decompose a of x to its factors. So what are the roots of a of x? So in order to be able to factorize it, I should know what are the roots of this polynomial. Well, one of them is -1, because as you can see, well, let's write it completely. So the roots of this polynomial are -7 plus minus square root of 7 squared minus 4 times 1 times 6 over 2, which means -7 plus minus square root of 25, which is 5 over 2. So there are two roots. Let's show one of them with x1. It's going to be -7 minus 5 over 2, which is -6. The other one is -7 plus 5 over 2, which is -1. Which means this polynomial x squared plus 7x plus 6 is equal to x minus 6 times x minus 1, right? We can do the same thing for the second polynomial bx.
Isn't it plus?
Sorry?
Isn't it?
Oh yeah, thank you. Yep, thank you. We can do the same thing for the second polynomial, x squared minus 5x minus 6. We can look at the, both of them. Yeah, thank you. So we can do the same for the second polynomial. X would be equal to 5 plus minus 25 plus 24 over 2. It would be plus minus 49. Its square root is 7 over 2. So one of the roots would be 5 plus 7 over 2, which is 6. The other one is 5 minus 7 over 2, which is -1. So this polynomial x squared minus 5x minus 6 can be written as x minus 6 times x plus 1. Now we should look for we are looking for the common factors. We have x plus 1 here, and we have x plus 1 here. So the greatest common factor divisor of ax bx is x plus 1. But now sometimes we want to use the other way, the Euclidean algorithm. I mean, in the question, it might specifically ask you to compute the greatest common factor or divisor using the Euclidean algorithm. So let's do that again. So we have x squared plus 7x plus 6, and we have x squared minus 5x minus 6. And I want to compute the greatest common factor. So the idea is, just like the case for integers, is to divide one by the other. So I should divide this one, the first polynomial, by the second polynomial. I should say this one is equal to x squared plus 7x plus 6 is equal to x squared minus 5x minus 6 times something plus something. So I should do this division. So let's do it. X squared plus 7x plus 6 divided by x squared minus 5x minus 6. Okay, so here the term with the highest degree is x squared. Here it's also x squared. So I just need to multiply it by 1 because 1x squared is equal to x squared. But then I have to multiply it by the rest of terms here. So I would get x squared minus 5x minus 6. Now change the signs here. It's plus, make it minus. It's minus, make it plus. It's minus, make it plus. X squared minus x squared, they cancel each other. 7x plus 5x is going to be 12x. 6 plus 6 is going to be 12. And then the degree here is less than the degree here. So that's it. You're done. So here the first polynomial in the first parenthesis is 1. The second one is 12x plus 12. Now, just like the Euclidean algorithm for integers, I should continue doing the same. I should divide x squared minus 5x minus 6 by 12x plus 12. Now, let me tell you something. In every ring, well, I guess you don't know what is exactly the definition of a ring, but here, see, we are working with some polynomials. Here, I'm assuming we are working with polynomials on the set of real numbers over R. I showed you R of x. So when I'm working with polynomials on R of x, 12 is a number which is invertible, right? So 12x plus 1 is 12 times x plus 1. And 12 is invertible. If I was working over qx, 12 is still invertible here. But if I was working with polynomials over zx, 12 is not invertible on zx anymore. So 12 is invertible in Rx because it's invertible in R and its inverse is 1 over 12. But it's not invertible, in Zx because 1 over 12 is not in Z. And whenever something is invertible, we can just kind of discard that. We don't need to write that. So here, rather than writing 12x plus 1, because 12 is invertible, I can kind of get rid of that. I don't need to write that anymore. I can just write x plus 1. Okay? So whenever something is invertible, we can kind of ignore that factor. So now I should divide. You can write 12 here too, it's fine, but you don't need to. So if it confuses you, you can just always write it. But well, all I'm saying is that you don't have to. So x squared minus 5x minus 6 divided by x plus 1. Okay, here I have x squared, here I have x. X times x would give me x squared. And then there is plus 1 here multiplied by x would give me plus x. I change the signs. I make both of them minus. X squared would cancel with minus x squared. Minus 5x minus x would be minus 6x minus 6. Here I have minus 6x. Here I have x. If I multiply it with minus 6, I would get minus 6x minus 6. And then I change the signs. They cancel each other. So here I would get x minus 6 plus 0. Just like the previous case in the integers, when we get to 0, we should look at the the previous remainder, which is this thing. That would be the greatest common factor. You can say 12 times x plus 1, or you can just say x plus 1. As I said, when something is invertible, which 12 over in R is, you can just ignore that. So the greatest common divisor or greatest common factor using Euclidean algorithm is again x plus 1. Any question? So let me just again tell you that if you're looking at these polynomials on Z, 12 is not invertible there. So I can't do anything about that. But now that if I'm, so I should here divide it by 12 times x plus 1. So let's do that. That's a good example. Let's now kind of solve the same problem, x squared plus 7x plus 6 and x squared minus 5x minus 6. Compute the greatest common divisor using Euclidean algorithm, but over zx. Now suppose these are polynomials in zx. Okay, so think about this problem for a few minutes and then I would solve it. Okay, does anyone know what's happening? There's a problem here. You should encounter a problem. Does anyone see the problem? Okay, let me explain. So we say actually Z is not a field. If you are not familiar with this board, it doesn't matter, but let me just explain what's going on here. So if I try to do the same thing over Z, let's see what's going to happen. So if I divide the first polynomial by the second one, again, I would get here 1 plus 12x plus 12. Now, over Z, 12 is not invertible. So in the next stage, I should divide this polynomial by 12x plus 12. But what is the result of this division? Can we do that? Let's see. If I want to divide it by this, what should I write here? Well, I want to kind of find something such that if I multiply 12x by that, it would cancel x squared. Can I find something like that? It should be something like 1 over 12x, right? But what's the problem with that? The problem is that this term here is not in ZX. Do you understand? Does it make sense? Yeah. So the problem is that this thing is not in ZX. So this, well, we don't have 1 over 12x. So we can't continue division. So actually, there is no division algorithm in ZX. We can choose Z here. The things we can choose are things like RX or QX, or, for example, Z2X or ZPX, but not ZX. Can you tell me what's the difference between these first 4 examples and ZX? What's the difference? Why we have division algorithm here, but we don't have division algorithm here. We can't divide polynomials in ZX, but we can divide polynomials in RX, QX, Z2, and ZP. Does anyone know why? What's the problem? Why we are allowed to divide polynomials in Rx, Qx, Z2, or ZP, where P is prime? The important thing here is that if you look at R, Q, Z2, or ZP, any non-zero element is invertible. Any non-zero element is invertible. So here, look at 12. The inverse of 12 is 1 over 12, also in Q. Or in Z2, we only have 0 and 1, and non-zero element means 1, and 1 is invertible. Or in ZP, we have 0, 1, up to P minus 1. Non-zero elements means 1 up to P minus 1. All of these things are invertible. There is another element, which if you multiply these two, you would get 1. And we have division algorithm in these spaces. These are, well, let's not, let's look at another example. So suppose you have x cubed plus 6x plus 7 and x squared plus 3x plus 2 in Rx. Use Euclidean algorithm to find the greatest common divisor or greatest common factor. Think about this one for a few minutes. Okay, so there is a question which says, I get that 1 over 12 is not an integer, so 1 over 12 is not in Z. But if x is a multiple of 12, wouldn't 1 over 12x be in Z? Are we just looking at the coefficient of x? So the answer is that, well, the answer is a little bit abstract. It might be a little confusing. But the point is that when we write 12x, we are not really thinking about x as a variable here. It's it's called kind of formal variable. What it means is that you shouldn't really think about kind of plugging in values in x. You should always think about it as 12x, where x is just a symbol, just a formal letter. So you shouldn't really think about what is the value of x at this stage. We just think about 12x as 12 times a symbol x. X is not We are not thinking about as like choosing a value for x. So the inverse of 12x, well, for example, well, 12x doesn't have inverse, but when in the previous case, I wanted to, I had, sorry, 1 over 12x. This is what I had. This thing, I shouldn't think about that if x is a multiple of 12. I just here think about x as like a symbol or a formal letter. And this thing is the coefficient. This is our coefficient, which is not in Z. Does it make sense? I think it might be a little bit abstract, but because it's different with what you see in calculus, for example, whenever in calculus you have a function or polynomial, when there is x, it means x is a variable. So you are allowed to plug in numbers in x. But in algebra, when we write 12x, we really don't think about x as a variable. We think about x just as a formal letter. Yeah, okay, good. Okay, let's compute the GCD here. So just like the previous cases, we are going to use Euclidean algorithm. So the first polynomial should be equal to the second one times 2. It should be times something plus something. So I should divide the first polynomial by the second one. The order really doesn't matter though. When I just say first and second, it's just some order I chose. It's okay. So here I have x cubed. Here I have x squared. If I multiply x squared by x, I would get x cubed. But I should multiply x by rest of the terms I have here. I would get 3x squared plus 2x. Let's change signs. Minus, minus, minus. X cubed and x cubed cancel each other. Here I have 6x. Here I have minus 3x squared. So I would get minus 3x squared. There's 6x here. There's minus 2x here. I would end up with 4x. And there's 7 there. So I would get plus 7. So here I have minus 3x squared. I want to cancel that. So if I multiply x squared by minus 3, I would get minus 3x squared, which is what I want. Minus 3 times 3x is negative 9x, and 2 times minus 3 is negative 6. So let's change the signs. This cancels with this. 4x plus 9x is 13x. 7 plus 6 is 13. Okay, now the degree here is 1. The degree here is 2. Degree 1 is less than 2, so we should stop. So here we have x minus 3, and here we have 13x plus 13. Now, the second step, we should write x squared plus 3x plus 2 here. We should divide it by 13x plus 13. It should be multiplied by something plus something else. What is the condition for stopping? Oh, at some point here, we should get 0. Whenever we get 0 here, we stop. Whenever we have non-zero remainder, we should continue. So here, 13x plus 13 is not 0, so we continue. Okay. So again, like the previous example, for the division, the condition to stop is that the degree here should become less than degree here. Here now the degree is 1, x to the 1. Here the degree is x squared. 1 is less than 2. so here I have 13x plus 13, just like the previous example. 13x plus 13 is equal to 13 times x plus 1. 13 is an invertible number in R. We don't really, when it's invertible, we don't really need to write that in the next stage. So I can simplify this to just write x plus 1. Still, if you write 13x plus 13, it would work, but it would be easier to write x plus 1. So let's do the second division. X squared plus 3x plus 2 divided by x plus 1. Here I have x squared, here I have x. If I multiply x by x, I would get x squared. And then there's plus 1, x plus 1 would be x. I change the signs. X squared and x squared cancel each other. 3x minus x is 2x plus 2. Okay, now here I have 2x, here I have x. If I multiply x by 2, I would get 2x. And then 2 times 1 is 2. I change signs, they cancel each other. I would get 0. So this is x plus 2 plus 0. Now I got to 0. Again, whenever we get to 0, the last remainder, the remainder in the previous stage is going to be the answer, which I can say 13x plus 13, or again, because 13 is invertible, I can just say x plus 1. So the greatest common divisor is x plus 1. Any question? Let's do another one to make sure we understand it. Say x to the 5th plus 2x to the 4th minus x squared plus 1 and x to the 4 minus 1 over r x. Yep. Can I go back? I think so. Is there any question here? Okay, so let's continue. So we have x to the 5th plus 2x to the 4 minus x squared plus 1 and x to the 4 minus 1. Find the greatest common divisor. Okay, let me start. So again, using Euclidean algorithm, we should write the first polynomial is the second one times something else plus something else. So I'm supposed to divide this polynomial by x to the 4 minus 1. Okay, if I multiply x to the 4 by x, I would get x to the 5th. So they would cancel each other. And then there's minus 1 here. Minus 1 times x would give me minus x. Let's change the signs. Here it's plus becomes, the first one is plus becomes minus. The second one is minus x, it becomes plus. X to the 5 and minus that, negative that, they would cancel each other. So what remains is 2 times x to the 4 minus x squared plus x. Now note that now the sign is positive, it's plus. And then there is plus 1 here. Okay, I have x to the 4 here, 2 times x to the 4. Here I have x to the 4. So I just need to multiply it by 2. I would get 2 times x to the 4 minus 2. Then I change the signs. This would cancel this. I would get minus x squared plus x. Here I have plus 2, here I have plus, here I have plus 1. Sum would be plus 3. So x plus 2 would come here. Minus x squared plus x plus 3 would go there. That would be the first step. In the second step, we should divide x to the 4 minus 1 by minus x squared plus x plus 3 by this thing. So the second division would be x to the 4 minus 1 divided by minus x squared plus x plus 3. Okay, here I have x to the 4, and here I have minus x squared. So if I multiply it by minus x squared, minus times minus would become plus, and x squared times x squared becomes x to the 4, which would cancel the other x to the 4. Minus x cubed minus 2x squared. Maybe I should write it a little bit on the left. Let's change the signs. Minus, plus, plus. These would cancel each other. I would get x cubed plus 3x squared minus 1. Okay, here I have x cubed, but here I have minus x squared here. So if I multiply that by minus x, I would get x cubed minus x squared minus 3x. Let's change the signs again. These two cancel each other. 3x squared plus x squared would be 4x squared plus 3x minus 1. I should continue this division one more step. Because I don't have much space, let me erase these and move this thing a little bit up. So now I have minus x squared, but here I have 4x squared. Sorry. So I should multiply minus x squared by minus 4. I would get 4x squared. And then there would be minus 4x minus 12. I change the signs, minus, plus, plus. These two cancel each other. I would end up with 7x plus 11. Hopefully I'm correct. Yes, I'm correct. So here I would get minus x squared minus x minus 4. Here I would get 7x plus 11. Okay, let me erase all these things. Now for the next step, I should divide minus x squared minus x minus 4. I should divide it by 7x plus 11. I'm going to write it here, minus x squared minus x minus 4, dividing it by 7x plus 11. I would get, okay, so note that 7, we are in R of x. 7 is invertible. So if I multiply 7x by 1 over 7 minus 1 over 7x, 7 and 1 over 7, they cancel each other. I would get x. I would get x times minus x, it would become minus x squared. It becomes minus x squared. Then I have 11 times minus 1 over 7x, it becomes minus 11 over 7x. Changing the signs, these two cancel each other. I have 11 over 7x minus x. It would be 11 over 7 minus 1 times x, which is 4 over 7x. And then there is minus 4. Okay.
I have a question.
Let me erase the rest. Yes, sure.
Are you using the correct quadratic polynomial? Shouldn't you be using the minus x squared plus x plus 3?
Oh, okay. So let's see. First, we're dividing this by this. That was the remainder, right?
Yeah.
Next, this thing should come here. The remainder should come here. Oh, you're right. I'm making a mistake. Thank you for telling me. The second step, this thing should come here and this thing should come here. You're completely right. So let's change that. Plus x plus 3. Okay, so the first step wouldn't change much. We should multiply it with the same thing, and then we would have 11 over 7 plus x, which would be 18 over 7x. And then that term would be plus 3. Okay, is everything okay?
Yeah, I think it looks good.
Yeah, okay. So the next step, I want to cancel this term. So I should multiply 7x by 18 over 49. So if I multiply 7x by that, I would get minus 18 over 7x. And then I would have 18 times 11 over 49. And then I should change the signs. Oh, sorry, then this should be plus then. Becomes plus. I should change the signs, they become minus. These two cancel each other. We end up with 3 minus 11 times 18 over 49, whatever this number is. So here we get minus 1 over 7x plus 18 over 49. And here we get this number. Okay. It's good that if you all check to make sure there is no mistake. And if there isn't, we can continue. Okay, I guess this is minus 43 over 49, if I'm right. So the next step would be dividing 7x plus 11 by this number. But, well, this division is simple because this number is invertible, so I can just write its inverse. And this multiplication would be 1. Then I can multiply it by 7x plus 11 plus 0. Now, if you look, this multiplication would give me 7x plus 11, and the remainder would be 0. So we should stop. And the greatest common divisor would be this number. I think that's the number. I might have made a mistake, but it doesn't really matter. So the point is that this number over R is invertible. So it's the same as 1. Whenever something is invertible, we can just, in this process, we can replace it with 1, which means the greatest common divisor of these two polynomials is 1, which means these are co-prime. It means they have no common factor. So, you know, when we have two things which their greatest common divisor is 1, it means they don't have any factor in common, actually. So is it clear whenever we end up with such a number, when we are in R, a non-zero number, we can always replace these numbers by 1. We did the same thing in the previous question. We had 13x plus 13. We wrote it as 13 times x plus 1. I replaced 13 by 1. So I would get 1 times x plus 1, which is x plus 1. That's exactly the same thing. So here, this is something invertible, and therefore, the greatest common divisor is 1. Any question here? Now let's just look at one example about the inverse of a polynomial. This time let's look at Z2x. Z2 is a field, which means Z2 is, well, as I told you, we can do, well, the examples we care about in this course are Zx, Qx, and Zpx, where P is prime. So Z2 is a special case of Zp. Let's take these two polynomials. Let's say x squared plus 1 and x. I want to say these two polynomials are, one of them, well, each of them is the inverse of the other one. Modulo, well, okay. So let me first define something and then write it. Sorry, it would make more sense if I first define. So when we have a polynomial like f of x, say f of x is a polynomial, we can think about polynomials congruence classes mod f of x. Well, do you remember when we were working with integers, we used to say, for example, 5 mod 3 is the same as 2, or we used to say 5 is the same as 2 mod 3. This mod 3 here, this 3 is going to be our f of x. So for example, if f of x is 2x plus 1, I would say x squared plus 2x plus 1 mod this function, this polynomial 2x plus 1 is the same as x squared. Just like the case for integers, what we mean by this this notation 5 congruent to mod 3, it is 3 divides 5 minus 2. That's the same thing here. Here it's correct if and only if 2x plus 1 divides what we have on the left-hand side, x squared plus 2x plus 1, minus what we have on the right-hand side, which is x squared. This subtraction is 2x plus 1. 2x plus 1 divides 2x plus 1. So this is a correct statement. So, well, it's something we are going to continue next time. I think we have 2 more meetings, if I'm correct. So we are going to finish this thing next week. I guess we have another meeting. I'm going to review the course and solve some problems after that. Okay, is there any question? Is everything good? Any problem? Okay, if there is no question, that's it for today. Oh, there is a question. I think so. That's better to ask from Unhei, but I think the answer is yes. But it's better to ask her. Yeah, I would check with her before doing the review session. So, because it doesn't mention anything in the syllabus, I guess the answer is yes. So if there's no other question, well, that's it for today, and stay safe. Goodbye, everyone.